We should definitely not do that. But that's something maybe we have to do stuff.
Okay, welcome everyone. This is the last ITC lunch of the fall semester, so that means that the next meeting will be in the spring, which sounds like good news. Hopefully things will look warmer then, and we haven't had a big snowstorm as of yet, so we're still waiting. Yeah. So today we have some very interesting presentations. Oh, okay, yeah, that's the first title. That's Beane from CIMRI. I was trying to understand whether that's a political statement. GSC is innocent. Now, most of us don't know what it is, but he will explain. And then we'll hear from Brandon Parker from MSU. Where is Brandon? Oh, over there. He will tell us about on the prospects for our process nucleosynthesis in collapsars. Then we'll hear from Julie McGeoch from the CFA. I hope she's here. Oh, behind her? Over there, yeah, very fine. And Julie will tell us about a space polymer of glycine and iron, its potential role in accretion and detection via the JWST MIRI at 6.21 microns. And finally, we'll hear from a visitor, Amirnezam Amiri, who is currently at Arkansas as a postdoc. He's sitting over there again. And he will tell us about HOMERUN, a new multi-cloud method to accurately model emission lines in star-forming regions. Yes, tell us what GSC is.
Is the mic on?
Yeah.
Yeah, so hi everyone, my name is Gus. I'm a grad student here at the CFA. And today I'll be talking about the innocence of GSC. And as Avi rightfully pointed out, it would be helpful to explain what GSC is. So GSC stands for Gaia Sausage Enchiladas.
Well, that's still unclear.
So GSC is a satellite galaxy that merged with the Milky Way about 8 billion years ago, so redshift 1 to 2 or so. It was given the name Gaia Sausage Enchiladas. I don't know who gave it this specific name, but when it was discovered by two groups at about the same time. One group called it Gaia Enchiladas, which is like this beautiful like Greek mythology name. And then the other group took a different route and called it the sausage. So, of course, you have to give credit to both groups. So, one name that the community has landed on is Gaia Sausage Enchiladas, or GSE. It goes by other names as well, GES, GE/S, but that's not the important part of the talk today. So it is a satellite galaxy, so here it is. This is an in-body model that was developed by Rohan Naidu, who was a grad student here. And I'll play it forward. So in this simulation, the Milky Way is not shown, but it's like right at the center. And this simulation follows sort of the infall and disruption of the satellite galaxy. So the GSC is supposed to be responsible for constructing the interstellar halo. So the Milky Way has, the disk, which has this well-ordered rotation, but there's also a sort of diffuse halo of stars around the Milky Way. And it's supposed to have formed through merger events like this. And GSC is supposed to be the most massive, the most significant of these mergers. And so the interstellar halo is mostly composed of GSC material. And just to show, maybe to go back to that sausage name, the reason it's called the sausage is if you look at the interstellar halo in phase space, so this is radial velocity versus azimuthal velocity, it looks like a sausage. And this is showing updated data, so H3 data, and then the simulation, just to show that the in-body simulation is a reasonable match to the data. Now, so GSC is guilty of something, so it is guilty of shaping the interstellar halo, but GSC has also sort of been invoked in the literature as being the sort of main actor for resetting the Milky Way's metallicity. And in particular, the idea is that the material from GSC came in and diluted the metallicity of the Milky Way. So how do we know this? This is sorry, there's a lot of text on this slide, but this is a plot of the sort of chemical abundance plane of the Milky Way. Now the reason we like to look at this plot is because this is showing stellar surface abundance metallicities, and you can see that they're colored sort of by their age. And the surface abundance of stars doesn't really change over the course of a star's lifetime. And so what you're looking at here are actually snapshots in time of the gas phase metallicity of the Milky Way. And that's why we like to look at this plot. Now on the x-axis here is the iron abundance. And the iron is something that is sort of produced by every supernova. And so what happens is that over time the gas metallicity in iron will sort of increase with time as more and more supernovae contribute to enhancing the metallicity of the gas. Now the y-axis here is the alpha abundance over the iron abundance. And what this is showing is actually the fraction of supernova that contribute to the Milky Way. So what I mean is a higher alpha abundance means that there are more type 2 supernova, and a lower alpha abundance means that there are more type 1a. Now type 2 supernova go off immediately after star formation, whereas type 1a supernova go off over the course of billions of years. So the typical evolution in this chemical abundance plane of a galaxy is to sort of go down to the right. So as time goes on, more and more supernovae go off, and as time goes on, more and more 1A go off. And so as a result, the alpha abundance drops while the iron abundance increases. But if you look at the evolution for the Milky Way, and this is, sorry, I should have mentioned this is for the solar neighborhood. So if you look at the evolution of the Milky Way, you see that it's not such a simple track going down. There's a sort of like shift to the left at about sort of 8-ish billion years ago. And then the Milky Way goes down what's called a low alpha sequence. So it goes down that typical evolutionary path. And so what causes this shift? What causes this sort of bimodality in this plane? And the idea is that this is coming from GST. So GST came in, it brought its own fresh gas supply that's metal poor, dilutes the Milky Way. That's sort of the story. But the issue is when you look at the numbers is that they don't really add up. So the charge is that GST diluted the solar neighborhood metallicity by half a deck. And now if you do the math and say how much gas do you need to introduce to the system to make the dilution half a deck, if you assume GST brought in pristine gas, which is like the maximally good assumption for GST because it was definitely metal enriched, what you find is that the dilution factor is like 67%. What that means is that in the solar neighborhood, you have to replace 67% of the gas with pristine gas. So it's actually not really fair to say that GST diluted the solar neighborhood. It actually replaced the solar neighborhood. And this is hard to reconcile with the fact that the stellar ratio between GST and the Milky Way was something like 1 to 12. You can play with the numbers of it, because we don't exactly know what the Milky Way was like at redshift 2 or GST. But it's something. It's not like a super crazy equal ratio in stellar mass. And so the question is, where did this gas come from? And what the argument that we're sort of spiraling on is that it came from the Milky Way's own CGM. That it's actually the effect of the GST merger on the Milky Way CGM that reset the metallicity of the Milky Way. And so the CGM is the circumgalactic medium. So in the center here you have the disk, and there's sort of multiple processes in which the disk interacts with the CGM. So you have things like fountain flows where gas is ejected from the galaxy through feedback, most notably supernova feedback, and then it sort of falls back onto the galaxy. You also have in more violent episodes like outflows where the gas is completely ejected, mixes with the CGM at a larger radii, and maybe eventually falls back down. But importantly, you have this accretion. You have gas that accretes onto the central galaxy. And so we spent a lot of time working on a model of GSE. So here we have the Milky Way at the center. We have GSE. This is based upon that n-body model that I showed from Rohan's work. But we have GSE, we have a sort of truncated CGM, and then there's a CGM around the Milky Way. I'll show the movie. So as you can see, the disk in the middle grows as gas sort of flows in. The satellite sort of has its first parasitic passage, and then it has this sort of epicenter. It has these really violent explosions. Not sure if that's realistic, but the point is that the gas from GSE is sort of spread out, and smooth out across the CGM of the Milky Way, and then it sort of flows in, and then sort of gas, is continually accreting onto the galaxy. Now, if you take a look at just the net accretion onto the central disk, so the y-axis here is the amount of mass that came from the Milky Way CGM that is accreted onto the disk. You see, in the isolated case, a case where we don't have a merging satellite, you sort of have this net increase at the beginning and then a more steady increase in the amount of mass that's accreted. But if you include the merging satellite, you'll see that the total mass from the CGM that's accreted increases by quite a bit. Such that by 6 gigayears, the increase is something like 80% over the isolated case. So there's a significant change in the amount of gas that is accreted from the CGM. And I just want to emphasize, this is not mass that came from the satellite. This is mass from the CGM that was enhanced, whose accretion was enhanced by the satellite. So why is this happening? Well, it's helpful to look at sort of like a phase space plot. So what I'm showing here is radius versus radius velocity. And you see in the isolated case, especially in the inner region, sort of below 100 kiloparsecs, you see that the radial velocity is relatively small, in the order of like 20 or 30 kilometers per second. But when you include the merger, the radial velocity distribution is quite different. It extends much further down to about 100 kilometers per second. So why is this happening? Why is the radial velocity distribution so different? And the answer has to do with the temperature distribution of the gas. So in the isolated case, the gas is sort of sitting at like 10 to the 5.3, 10 to the 5.4 Kelvin. It's in this relatively hot phase. But when you include the merger, this gas that extends all the way down to 10 to the 4 Kelvin at the same radion. And of course, if your gas is cooler, a low temperature gas has lower thermal pressure support, and so it's able to infall at a much higher rate. And of course, now this is sort of thinking another one. Why is there a low temperature gas in the merger case? And what we think is happening is that it's something that is called like stimulated accretion. So the idea is that cold gas from GSE mixes with gas from the CGM, and that causes the gas from the CGM to sort of go up the curve. Because at these temperatures, the cooling curve is increasing towards lower temperatures. And as a result, you get more and more gas that's cooling down to lower temperatures. So the idea is that you have cold gas from GSE, hot gas from the CGM. They mix, they make warm gas, but warm gas cools much more efficiently than hot gas. And so you just get more and more cold gas in the CGM. Okay, so this is all well and good, but what I've described so far is kind of like basically vibes. Like this is kind of a story. And so, it's really hard to sort of come up with an isolated simulation that includes all the sort of realism and context that you have in a real galaxy. And so, just this past week, we've started to look at to see if this picture that we've come up with, whether it holds true when we look at the galaxies in electricity and G. And so, I've been looking at galaxy 523A89, which is everyone's favorite galaxy in TNG. But I'll just quickly say that this galaxy, it doesn't have a striking biomodality, although if you plot it in a certain way, you might be able to get one. But it does have structure in the chemical plane. And if you look at the time evolution of, this is showing the time evolution of the stars in this chemical plane. So this is, as you go along this track, you're looking at younger and younger stars. You see that it goes through these sort of like loop-de-loops. So I'm calling this the chemical roller coaster. And there is a merger in this galaxy, but it happens like up here. And it gives rise to, it looks like, essentially 4 metallicity resets. And so the question is, what is actually causing these metallicity resets? Why does one merger lead to 4 loops? And so on. And this is sort of stuff that I've just started looking into. So that's pretty much it, yeah.
Bringing this closer to home, how was the sun affected by this merger? Was it triggered by the merger, or based on the metallicity of the sun?
Yeah, I mean, it kind of depends on where the sun was born. Because something that I didn't get into in this talk is that the bimodality actually only happens in the outer disk, like beyond like 6 or 7 kpc.
We are at 8.
We're at 8, but if you believe the people who say we were born at 4, then
okay.
Yeah.
But we were born 4.6 billion years ago. When does this happen?
So the merger happened about 8 billion years ago, and so that's kind of when the reset is supposed to have happened. So it would have happened before the sun was born. So the sun should be on the low alpha sequence, that lower. Yeah.
But there should have been a star formation peak around that time.
Yeah. Yeah. That's what one would think. But
Okay.
yeah.
Questions, comments, please. Evan.
So in this awesome movie, I have to ask about when GSE appears to spontaneously explode after the very summer passage. Is that like because of an episode of star formation stimulated by the first very center passage, or do you have a sense of what's going on there?
Yeah. I mean, I don't super believe that because like the model doesn't seem. So this uses the Smuggle model, which was kind of calibrated on like redshift 0 Milky Way like galaxy. And it hasn't really been tested in this sort of much more gas-rich, violent environment. And in particular, it seems that the sort of the like early feedback, which is the like radiation pressure, basically the feedback that happens before the first supernova goes off, is not efficient enough. And so that means that basically the supernova feedback is less efficient in dense environments. And so what might happen is sort of the gas is sort of collapsing to denser and denser values. And then you get more and more and more, stars, or young stars that are forming, until eventually everything breaks, and then you get like this violent explosion of gas outwards. Yeah.
There's another question. Go ahead.
Is there any evidence that the merger caused any change in the activity of Sagittarius A star? Because I would imagine if Sagittarius A star became active, then it would offset this cooling effect that heat the gas back up, and that would do the opposite thing to the cooling gases.
Yeah, that's an excellent question. So It is true, actually, in the simulation, basically, you know, the satellite sort of comes in on the second parasitic passage. It sort of comes in from below and impacts the early disk and sort of torques the inner disk, and torques the inner disk. And it causes this sort of compression of gas in the central 2 kpc that causes a starburst. That's you know, on the order of a few solar masses per year in that 2 kpc region. And so it's not unreasonable to think that that might fuel an episode of Aegean activity in Sagittarius A star, which might, yeah, you're exactly right, which might sort of influence the accretion of gas onto the galaxy.
And also probably trigger a different path because of the timing.
Yeah, there actually was a paper like yesterday or 2 days ago that looked into this, basically looking at a GSE-like merger in the Auriga simulation, where they remove the galaxy actually from the zoom in and to see if it sort of delays the onset of the bar, and it takes like 1 or 2 billion years more. But I think I think it's like to be like very precise, I would say it didn't like cause the bar to form, it just sped up the bar's formation. Because the galaxies, like, you really need like a really like major merger on a prograde orbit in order to trigger a bar that wouldn't otherwise form. So you know, the disk was probably sort of susceptible to bar formation in the first place. It was just hadn't formed yet, and GSE helped it along.
So would the presence of cold mode accretion at redshift 2 for the Milky Way change the amount of metallicity reset that you can give to the galaxy?
Would it change the amount?
So like basically with the CGM accretion mode of the Milky Way at redshift 2 significantly affect how much metallicity is reset?
Yeah. So this argument sort of relies on there being sort of a reservoir of hot gas in the CGM, and that may or may not be true at redshift 2 for the Milky Way progenitor. That's very true. So there is, however, still going to be a gravitational effect, because the gravity of GSE will deepen the potential, and that will cause the fault to increase. So that, you know, between a merger and non-merger, you would have different evolution. Yeah.
Last question, Tony.
Or in your model, do you have gas which is not the result of a merger? In other words, gas which is just simply primordial gas coming from the Big Bang that is still falling in, not connected with an actual merger with another galaxy?
We don't have like the system is basically like a spherical CGM in both cases. The Milky Way CGM goes out to like 300 kpc, and then the satellite is cut off at 30 kpc, which we can, in principle, make that larger if we sort of move it back in time. But we don't include accretion from beyond 300 kpc. And I mean, beyond the virial radius, probably the spherical assumption is not very accurate. So, yeah.
Let's thank Gus again.
I'm a final year graduate student at Michigan State University, and most of the time now at Los Alamos National Lab. And I'm going to chat about some stuff that we've been doing at the lab concerning our process, nucleosynthesis, in magnetorotational supernovae, and hopefully convince you that there's some very exciting things on the horizon. So just as a little introduction, broadly, something I'm interested in is nuclear astrophysics, which is this beautiful world where we need fundamental nuclear theory, nuclear experiments to understand the nuclei that are made. We need stellar spectroscopy to understand what abundances do we actually observe in the universe. We need simulations of these sites that might produce heavy element nucleosynthesis, and then other observables like gravitational wave and electromagnetic emission to hint at more at what is made. And for me, I'm particularly involved in the simulation side, understanding what is the physics that drives these nucleosynthesis sites, these explosive astrophysical sites, and then how do we connect that to these other pieces of the picture. And it's a very exciting time to be thinking about our process, nucleosynthesis. Since gravitational wave 170817, we now know that neutron star mergers are a definitive source of our process nucleosynthesis with the joint observation of the gravitational wave event and kilonova emission. However, the picture is more complicated. Looking at, for example, ultra-faint dwarf galaxies, it seems to be that there needs to be another R process site, something that operates on much faster timescales of prompt source. So, for example, Reticulum-2, most of the stars are super metal poor because it's very old, but they show an immense R process enrichment that is very hard to explain from neutron star mergers. And so the commonly accepted picture is that there needs to be another site that operates on prompt timescales, and usually it's rare subclasses of supernovae that are invoked to do this because supernovae are going to happen on timescales faster than neutron star mergers in general. For some of these rare subclasses of supernovae, what we think of is the collapsar picture. So these come from rapidly rotating, highly magnetized progenitors that might be the progenitors of long gamma ray bursts. So when these things collapse, we form a black hole in their core, and then the infalling stellar material, because it's rapidly rotating, is going to circularize into an accretion disk around that newly formed compact object. And you get relativistic jets that have to puncture through the stellar material, they break out, you get a gamma ray burst. And these are super exciting as a potential R process site because they're not that different from neutron star mergers, right? You have compact object accretion, you have stellar material that is potentially neutron rich depending on the model. And so they've been thought about it a long time as a potential R process site, and there's been some really exciting stuff happening since 170817 on this path. So a few years ago, Dan Siegel did a bunch of models where varying the mass accretion rate did accretion onto a black hole with some surrogate, we'll get into that in a bit, collapsar models, and then did the nucleosynthesis from those. And what Dan and them found was that if the accretion rate is high enough, you can get a full R process, robust, beautiful, everything is solved. They estimated like collapsars are something like 80% of the R process source. The picture is more complicated because physics is more complicated. Our group at the lab redid the exact same scenarios, the exact same models, but with more realistic neutrino transport. Neutrino transport is important because neutrino emission and absorption adds or removes protons or neutrons from the source, right? And so you can get more neutron-rich or more proton-rich material depending on the neutrino physics and how it interacts with the matter. And so what we found when we did this was that if you increase the fidelity of the neutrino transport, you don't get neutron-rich material in the collapsar. You might get a first or second peak R process, but even in the most optimistic case, there is no third peak R process in these collapsar models. And so the neutrino transport is super important. From the supernova side, this is not too surprising, right? But there's another problem with these models, and that's the initial conditions. For these collapsar models, what is traditionally used are the so-called fishbone Moncrief tori, where you initialize a torus around the black hole or compact object, allow MRI to spin up some turbulence, you get accretion, jets, etc. And this is super great for traditional black hole accretion, right? The problem is that it's atmosphere or vacuum outside of the torus. There is no infalling stellar mantle to feed the disk, there's nothing to puncture through. The dynamics are very different. And so we're missing a lot of physics with these models, right? Even if we, in the most optimistic case, say, oh, we get the whole R process. There's no way to say, is it actually ejected from the system? Because it still has to puncture through an entire, maybe 10 solar masses of envelope. And so it's much harder, and there's a huge need for realistic initial conditions in this world. This has happened recently. Moore Gottlieb and folks at Northwestern and collaborators have done this, where they use a more realistic stellar profile, follow self-consistently the infall of stellar material, circularization of the disk, formation of the jets, and all of this. And they get these beautiful results where they follow the jets all the way to the breakout from the stellar surface and do really great work. The problem with this is that they don't have neutrino transport, radiation transport, or accurate microphysics in their models, and so you can't do any nucleosynthesis with these models. So we have these two diverging or parallel pathways where we have really good neutrino physics, but bad initial conditions, and really good initial conditions, but not the right microphysics or transport to do nucleosynthesis at all. And so that's where we really need to go as a community, and I'm going to convince you that this is coming very soon. But why hasn't it happened? These things are huge, complicated, but beautiful problems, right? We have a huge amount of physics to implement in this model. General relativity, neutrino, or generally radiation transport, that we've shown has to be really robust, complicated microphysics from dense matter equations of state to neutrino matter interactions, or photon line opacities if you're doing photons, to MHD to drive the turbulence in the jets. And these are all coupled across a huge range of temporal and spatial scales. So it's a really hard problem, right? In a perfect world, we need to resolve the turbulent dissipation scale, magnetorotational instability, all the way out to like stellar radii. The central engines are going to operate on timescales of milliseconds to seconds, whereas observable timescales are days to months. Shock breakout in a traditional red supergiant is a day-ish. So there's a huge range of scales that, to do this correctly, we need to resolve them all. And that makes it a really hard problem, right? There's a lot of really cool stuff happening in the lab. We've developed this new code called Phoebus, which has a really fun acronym that I didn't put on here, but I'll tell you about it if you ask me. That is being developed right now broadly for problems in relativistic astrophysics. So Phoebus broadly is a general relativistic radiation magnetohydrodynamics code. It has a lineage that is pulled off of Athena++, so we have its software development under us, supporting us. And we're striving to be performance portable, which means, as we'll see in a minute, that we can ideally run on any computing system out there, be it GPU, CPU, NVIDIA GPU, AMD GPU, whatever, use it and use it efficiently so that we can keep up with the changing computational world. And we're developing this right now for core collapse supernovae, mergers, black hole accretion, and maybe your science application. We're really excited to start working with people if they have other interesting ideas for what to do with this. Looking a little bit, the plot here is performance with Phoebus. The top line is a weak scaling plot. All you need to know is that it's a function of the number of nodes on the computing cluster, up to 1,000 to 10,000 nodes, depending on the computing architecture, and that a flat line is perfect parallel scaling. So we get, in the best cases, something like 90% parallel efficiency on 10,000 frontier nodes. And the two sets of lines are CPU and GPU. So we have something like an order of magnitude performance increase going from CPU to really utilizing these heterogeneous architectures. And the movie here is one of these, a test problem with one of these fishbone Moncrief tori run with Phoebus with tracer particles overlaid, which we'll use later to do nucleosynthetic post-processing. And so that's what we have been doing. I would really like the next slide to be beautiful collapsar simulations, but we will probably start those next month, unfortunately. But coming soon with Phoebus, right now actually we're running full physics black hole accretion models with photon radiation transport. We will be doing the full physics collapsar simulations with realistic initial conditions to constrain our process yields in the very near future, doing a grid of models across different stellar progenitor parameters. Collaborators and I are also super interested in traditional 3D core collapse supernovae with state-of-the-art general relativity and neutrino transport to really nail down what is the explosion mechanism for these things, and then later down the line getting in situ nuclear burning and fun things like this. I'll put up my summary and I'll take questions. Just to say that Phoebus is going to be doing some really cool things, and hopefully I'll convince you that there's very exciting stuff coming in the near future for all of relativistic astrophysics. And also the code is open source on GitHub. Anyone can take it and look at it, and the paper will be out very soon, hopefully.
So, Brandon, in your mind, obviously there are various sources that were proposed for our process advances, including neutron star mergers and supernovae, some types. So what do you think is the split among those?
I think it is clear that neutron star mergers are probably the dominant source. The rates of these rare supernovae are low already, So even if every single one produces a robust R process, they're going to be low. In my mind, we will not see a robust R process for the most optimistic models, but it remains to be seen.
But you will not see also a signature in the long gamma reverse from the production. Very heavy evidence.
I think it's possible to find a signature if we have a robust R process, but I don't know that we will see it.
Okay. Ramesh.
Yeah, thank you for this
Uh-huh.
nice introduction. I've heard of FIBOS
Yeah.
from my colleagues at Los
Uh-huh.
Alamos. So you mentioned that there's this big disparity of time scales.
Yeah.
And the black hole time scale where all the action is happening versus what the observer is seeing. Are you actually going to bridge that whole range of time scales and length scales? Or are you still going to be, you think, only focusing on the inner, maybe 1,000 gravitational radii?
The initial work is going to be on the inner few thousand gravitational radii. Long term, I do want to get beyond shock breakout and comparing to actual observations with spectra and things. But that's a long-term goal.
Yeah, is it even doable? Even the GPUs?
I think so, but there's games that you have to play. I've thought about this the most for traditional core clock supernovae, but the problem is the same. And that at some point, for example, the radiation transport is not important. The neutrino heating is done, you can turn it off. There's a huge gain in computational cost right there. And then you remove the black hole or protoneutron star and just let it go. And that's been done for traditional core clock supernovae and is a solvable problem, but it is a large computational challenge. So, with games.
Several years ago, probably more like 5, in the early days after 1708, Brian Metzger and somebody, and I don't remember who the somebody was, sorry, claimed that black hole collapsars could dominate protoneutron star mergers.
Yes.
What did they, is this?
That was the reference that I showed on a previous plot. It was Dan Siegel and them. And the,
So what did they do wrong if you think it's not the
yes,
most important process?
is the neutrino transport.
Yeah.
Their transport algorithms were super not sophisticated. And when you do more accurate neutrino transport, it doesn't produce neutron-rich material.
Good, thank you.
By the way, the speed by which the ejector moves also depends on the source. So is that an important factor or not? It gets mixed with the interstellar medium to different distances.
I think it's important. How important it is, I'm not sure.
Okay, no more questions. Let's thank Brandon again.
Hello, I'm Julie McGeoch from CFA, and previously I was in molecular and cellular biology.
We
2
cannot
years.
hear you very well. Do you have the mic on? Oh, maybe
Switch on.
Sorry about that. Start again. Hello, I'm Julie McGeoch from CFA, and before that I was in molecular and cellular biology. I work on a polymer that derives from asteroid sources, and in this talk I will describe how eventually we're going to hopefully detect it via the James Webb telescope. First I will describe why I'm doing this at all. in 2008, I was working on the structure of a hydrophobic protein, which is the rotor part of the molecule in biology that produces ATP, your energy source. And it did not behave like a protein. It behaved more in certain conditions like material, in that it entrapped water. And the water was perfectly ordered so that there was only 1 picometer of error. And this is an image of the protein as beta sheets. And I thought, if a protein, which is basically CCN, which is a molecule which is both flexible and stiff, and therefore might be able to survive in space, if it can entrap water, it could act as a beaker. I therefore did quantum calculations on the polymerization of protein. Now there are 5 states to the polymerization of protein. And the transition state is a huge barrier to any protein forming in gas phase space. However, when protein does polymerize, it ejects a water molecule when 2 amino acids meet. And that water molecule always hydrogen bonds back onto the protein and lowers that terrible enthalpy barrier. Here, meaning that it might have been possible. Therefore, I went to various sources in carbonaceous meteorites, and on the left there are 6 meteorites listed, all of which contain this polymer. In the middle there is a fossil stromatolite. Now that 2 billion years ago was under an ocean in Montana, and on the right there is present-day stromatolites, and they're ooids, which are the smaller components of a present-day stromatolite. All these contain the polymer hemoglycine. Its basic structure is a core molecule that is 5 nanometers long. It's 1 antiparallel beta sheet of protein separated by iron. The methods we use are to extract the polymer from particles, use a 2-phase chemistry Fulch extraction system. We use mass spectrometry amino acid analysis, X-ray diffraction for structure and for the visible absorption, extraterrestrial isotope detection by MALDI and FIB-TOF-SIM, and for IR absorption, which is the more important part of this talk, we use FTIR in a synchrotron or in SIMS at Harvard. We also use powder diffraction. The molecule forms a very low density extensive lattice. This shows what we have detected this structure in the Asper meteorite and in Shark Bay ooids from present-day stromatolite. It's basically a diamond 2H structure. In that lattice, it is absolutely ideal for the accretion of matter. And this is a diagram outlining that. A 3-dimensional hemoglycine lattice with the diamond 2H structure, and its contents could be very small grains, 6 to 8 microns emissions. And high and low lattice vertices are labeled. This slide shows a crystal on the top left, which came from the ASFA 086 meteorite, and it shows the accretion of nickel at 2 angstroms, 1.7 and 1.5. Most important part of the function of this polymer is that it absorbs visible light and IR. This is quantum calculations for its visible light absorption. Now, proteins in biology have a chirality, unless they're glycine, which has no chirality. And they're all levorotary, or LS. This abiotic molecule has a dextrorotary rectus chirality. So the top graph shows no absorption at 480 nanometers when it is the S chirality. When it is the R chirality in the bottom graph, it does have absorption at 480. We therefore went to the diamond synchrotron in Oxford and measured this in crystals. On the right is a crystal of from the Sutter's Mill meteorite, and that shows on the left its 480 nanometer absorption. Further, this is structural data from that crystal. The distance, the single distance for any one of the core proteins is 4.9 nanometers iron to iron in the hemoglycine, and that gives rise to 13 diffraction orders. Basically, these are the 4 components for the many forms that hemoglycine can form. Number 1 is the core molecule of 1494 Daltons. It shows the never mind. It shows the top number 1 basic molecule with iron to iron 4.9. Number 2, a slightly larger form of the molecule because it has more iron and oxygen. And the vertices always contains, or nearly always contains silicon. It either has 2 bonding positions or 4 bonding positions. So now I go to the quantum calculations for the IR absorption. The core molecule is shown at the top, and the protein part has an amide 1 and an amide 2 area, which absorbs at 6.2 micrometers. The amide 1 is a C oxygen bond, double bond to oxygen, and the amide 2 is the basic CN of the amide bond, or a carbon, the alpha carbon with 2 hydrogens. And also at 3 microns there's the NH stretch. This is the experiment for the IR absorption. On the left from the Sutter's Mill meteorite, and on the right from a stromatolite from a present-day ulite. The blue triangles show the amide 1, orange the amide 2, they're both present in both. The NH stretch, which shows in the meteorite, and for both of them there is the accreted material, the calcium carbonate, which is shown by the yellow. So our aim is to go to 2 very bright stars in our galaxy and use that to backlight a molecular cloud, where hopefully we will be able to detect it. On the left we show IR absorption in the meteorite, the Sutter's Mill meteorite, and on the right we show work that was done in 1998 by Shute from the ISO observatory, where they measured 6.2 and attributed it to polyaromatic hydrocarbons. The small graph superimposed at the top is polylysine absorption measured in a laboratory. All proteins that have anti-parallel beta sheets, like hemoglycine, have this 6.2 absorption. The evidence that hemoglycin presence from other astronomical observations would be PAHs and the extended red emission and potentially the UV bump. I'd like to acknowledge the following people. The late Guido Guidotti, I worked in his department in molecular and cellular biology, starting all this work. The other people in the list are all related to instruments I use. The meteorites are then listed. Fossil stromatolites came from David Lagson, the present-day stromatolites from Andrew Knoll, and my colleagues are Malcolm McGeoch, who helps with determining the mass characteristics of the molecule, and Matt Ashby will be my co-PI if we get time on MIRI. And I'm very grateful for funding from CFA. Thank you.
Hopefully the reviewer of your proposal is in the room. So. Some people suggest that with quantum computers it would be possible to actually do quantum computations, predicting the spectra of very complex molecules much faster. Do you have anything to say about that? Rather than doing it in the lab?
Yes, it would be useful for doing the entire molecule, which is very large.
Right.
And I would love a student to take that on.
Okay, any student?
I have a pending NH grant, and they could definitely work. It would be wonderful.
Yeah. Comments, questions? This is traditional molecular atomic physics, and we don't often hear such detailed talks on this subject. So thank you for presenting it. Let's thank Julie again.
Hello everyone, it will be a great pleasure to be here. I am Amirnezam Amiri and I recently finished my PhD at the University of Florence in Italy, and I currently am a postdoc researcher at the University of Arkansas. And today I want to speak about a new multi-cloud method to investigate about the gas-phase metallicity in the star-forming galaxies and the H2 regions. To investigate how galaxies are evolved, there are different few ways that we can study them. For example, the global items such as the coevolution between the central massive black holes and the galaxy stellar evolutions and so on. And all those items can directly affect the metallicity of the gas in both small and large scale structures. And it seems studying the gas phase metallicity in each classification can give us the highest information on how galaxies are evolving. To determine the gas phase metallicity, essentially there are two methods. We can directly use the information inferred from the emission lines in the spectra from the observational point of view that we can call it the empirical method, and based on which kind of the emission lines we can detect, it can be subdivided to the different methods. But one of the most important and precise ways to investigate or estimate the gas phase metallicity is based on the auroral lines. And sometimes people call it the direct method. For example, the oxygen 34363, oxygen 27330, and so on are the most important auroral emission lines that we can use in this method. The important thing about the auroral lines is that they are very sensitive to temperature. And because of this situation, they are very useful to estimate, to use for the estimation of the gas phase metallicity. But the bad thing is that they are too faint to observe. Regarding to the observational limitations, always people have been trying to do some kind of the simulations, mainly based on the photoionization models, to generate the spectra and investigate about the property that they can observe, and they try to find some statistical analysis to find the best coincidence between what they have in the computational aspects and observations. In the last 2 or 3 decades, people have been used statistical analysis to find this kind of the coincidence with the name of the single cloud. It has been shown that any given emission line will be optimally emitted at a specific ionization parameter and the critical density. For example, thus a weighted average over the ionization flux and the critical density can include gas with the optimal properties for emission lines with a specific ionization parameter and the number density. But the main thing is that in the all single cloud aspects, for example, local optimally closed emission lines and so on, we cannot provide both low ionization and high ionization emission lines simultaneously. And if we want to investigate about the gas phase metallicity, for example, based on the auroral lines, we need to provide both low ionization and high ionization emission lines at the same time with a good order. So if we look at, for example, a star-forming galaxy here, when we are studying the spectrum of the galaxies, it means that all of the emission lines are propagating from the different parts of the galaxies, and at the end we have an integrated flux. For example, in this case, we can see that a star-forming spiral galaxy is not a unified single cloud, and we can observe a large number of the different H2 regions where the new stars are born, and each H2 regions has a specific initial physical conditions to provide the emission lines. For reconciliations and providing the both low ionization and high ionization emission lines simultaneously between the observations and the computational aspects, it means that if we think about some kind of the multiple cloud statistical analysis, it would be more beneficial to provide those emission lines simultaneously to estimate the gas phase metallicity. So from this case, we need to do 2 items. From the simulations aspects, we are trying to generate the spectra by the photoionization modeling called Cloudy. Cloudy is an open source microphysics and plasma based simulator, and the goal of the Cloudy is to simulate conditions at the non-equilibrium gas to provide or generate the spectra, the thermal state, level of the level of the population, and ionization state of the gas. And the good point regarding the Cloudy is that we just a few initial parameters as an input. For example, the geometry, the number density of the hydrogen, the ionization parameter, the gas phase metallicity, and the spectra. We can provide a huge number of the simulated the spectrum from the different for the H2 regions and star-forming galaxies with a different property. Regarding to some initial conditions with this aspect, we can approximately more than the 10,000 spectra that they can describe the different H2 regions and star-forming galaxies. So it is very important before speaking about the multi-cloud and verifying our photoionization models, so it is very essential to find a sample of the galaxies to cover the main auroral lines from the low metallicity to high metallicity to investigate about that. For those galaxies, for the low metallicity, we are using galaxies from the STS SDR7 by the Courtier tool in the 2019. Approximately, regarded to some conditions, where we could find around of the 400 galaxies with the low gas phase metallicity that we could detect the auroral emission lines for those to estimate the gas phase metallicity. But whenever you are going to the high metallicity, the auroral lines are double to faint, and because of this situation, you need to do some kind of the stacking procedure to detect the auroral emission lines. For the high metallicity, we consider approximately 70 galaxies, stacked galaxies, based on the Courtier tool 2019. So here you can see that how much an auroral line can be faint, as you can see here, regarding to one of the polymer series. And one of the very important emission lines that we need to estimate the gas phase metallicity is the oxygen 34363. That you can see how much they are different from the main emission lines. So from the one part, we have a bunch of the spectra from the cloudy simulations, and from another side, we have a lot of the galaxies with auroral lines that they can cover the gas phase metallicity from the low to the high. And what can be a multi-cloud? To find which kind of the photoionization models can reproduce all observed emission lines in both single galaxies and stacked galaxies, we consider a linear combination of the photoionization models. We consider a grid of models which varies in both ionization parameter and number density of the hydrogen at a given stellar continuum shape and gas phase metallicity of the grid. And then the best models are the combination of the weights, the weighted combinations of the luminosity of each grid. And the idea behind this approach is if a model can reproduce all observed emission lines, it means this model can reproduce the right occupied volume at the right temperature. And if you are in the right temperature, it means that you can estimate the abundance in good way, and you can estimate the gas phase metallicity with good precision. So here, for one of our galaxies, you can see that how chi-square varies as a function of the metallicity of each grid, and we have a clear minimum at the right gas phase metallicity of the model. The vertical dotted, the dashed blue lines are the result of the multi-cloud approach. The red color is demonstrating the gas phase metallicity for our observation based on the T method that we say that it is one of the most precise ways to estimate the gas phase metallicity. And this is the estimation, and this is the predictions if you use the previous model based on the single cloud. So it seems that the multiple clouds can provide the gas phase metallicity in a very good and precise way. So if we consider that the single galaxies at low metallicity are the green and the blue are related to the stacked galaxies, in around of the 10%, we could provide both high ionization and low ionization emission lines based on the multiple cloud. And you can see here the 4 different emission lines, species, for example, nitrogen 2, sulfur 2, oxygen 2, and oxygen 3, that based on the multi-cloud, you can provide both ionization states simultaneously. That in the single cloud previously, we could not provide those. So it seems that not only related to predicting the low ionization and high ionization emission lines, but also for other quantities, for example, the behavior of the global ionization parameter as a function of the gas phase metallicity and other correlations between the esterine calibrations and the T method based on the multiple cloud approach is fine, and this is code.
Questions to Amirnezam? Yes, go ahead.
There's a long-standing problem that you get different abundances using recombination lines and collisionally excited lines, individual HQ. Can this body solve that?
I don't think so. No, we cannot provide. But the one thing that probably we can do is in the different cloud simulations, you can use the different abundance based on the different property, and you can combine them. But the fact is that in the cloud you cannot do it directly.
In the example you showed, there's the single probability that was way off in the low end.
Actually, this is the worst case.
Yeah, but generally, if it's the same trend, does it mean that we generally over-predict the number of low metallicity galaxies or use the same problem models?
Yes, actually, this is if you go to the low metallicity, the single cloud result is very near to the multiple cloud result. But in the high metallicity, we have the main problem with the single cloud, and this is the point.
Any other comments, questions? If not, I wanted to wish everyone happy holidays, and we'll see you at the end of January.